Hey guys, Mr. Betts here. When we're evaluating antiderivatives, usually it's going to be for the purpose of evaluating a definite integral. So I want to take a look at this process of substitution with antiderivatives and look at how we can modify it a little bit to help us with finding definite integrals. So in this problem, in the previous video, I went through the antiderivative of cosine of x times sine of x cubed. And what I'm going to do is look at that with how we would apply that to a definite integral. Keep in mind, to evaluate a definite integral, we start by finding an antiderivative. So I'm going to do the same thing I did and choose u, take the derivative of u, and for the purpose of substituting for the dx, I'm going to solve for dx. And so now I'm going to make the substitution. So we have the antiderivative of cosine of x times u to the third power times du over cosine of x. The cosine of x's are going to cancel each other out. Now, this would be a bad equal sign right here. So the problem with this equal sign is this expression right here is a definite integral, which represents an area, which is going to be a number. This right here is an indefinite integral, which is going to represent a function, specifically a function that if we take the derivative, we get back to where we started. So this equal sign is bad right now because we have a number equal to a function where we should have a number equal to a number. So what I need to do is I need to carry along these limits. But the problem we have here is that these limits are telling us that we're going from x equals 0 to x equals pi over 4. And when I change my differential to du, now it's going to look like we're going from u equals 0 to u equals pi over 4. So what I'm going to do is I'm just going to write x equals 0 and x equals pi over 4, just to remember that this definite integral is with respect to x and not with respect to u. It is important that we have the x equals in front of these because this differential right here is telling us what the independent axis is. And if we have a du there, these should be u values unless we say otherwise. So then the next step with our antiderivative is going to be taking the antiderivative, u to the fourth over 4. Now, remember we have a plus c there, but we're doing a definite integral, so we need any antiderivative, and we can choose c to be 0. But we do need this x equals 0 and x equals pi over 4. Again, those are x values, and this expression here is in terms of u, so we need to keep those x equals on there. Now we can substitute back. So substituting back, we get sine to the fourth power of x over 4, evaluated from 0 to pi over 4. And then we can actually substitute those values. Now, notice that I left the x equals off at this point because our expression is in terms of x, and those are x values. So we can infer from looking at the work, or imply with our work, that those are x values. So now we're going to have sine to the fourth of pi over 4 minus sine to the fourth of 0 over 4. So sine of pi over 4 is going to be, so pi over 4 is a 45-degree angle. So sine of pi over 4 is going to be 1 over square root of 2. 1 over square root of 2 to the fourth power over 4 minus 0. So sine of 0 is 0. So 1 over square root of 2 squared is going to be 1/2. And then that squared again is going to be 1/4. So we end up with 1 over 16. So this process is okay, but we have some kind of clunky stuff going on here with our limits and changing the variables. We have to make sure that it's clear that our limits are x values instead of u values. And so what we can actually do is, when we make the substitution from x to u, in order to avoid writing x equals pi over 4 and x equals 0, we can change those to u values. And that's actually going to save us another step at the end. So let's take a look at that process. So with definite integrals, this should say definite integrals here. So with definite integrals, we're going to choose u and differentiate u and substitute mostly the same way. However, the last part here with our substitution is going to be a little bit different. All right, so let's go through those steps. So we'll say u equals the sine of x, du equals cosine of x dx, dx is equal to du over cosine of x. So making the substitution, we're going to have, we've got u is sine of x, so it's going to be the integral of cosine of x. Sine of x is going to be replaced by u, so u to the third power. Dx is going to be replaced by du over cosine of x. And just like we've seen in previous problems, actually this exact same problem previously, the cosines cancel. But then the last thing we're going to do here is we're going to change the limits also. So when we change the dx to a du, we're going to change these to u values. So remember, these are x values right now, and we have an equation that we came up with that relates x and u to each other. So if x is 0, then u, plugging 0 in for x here, u is also going to be 0. So that lower limit stays the same. However, with our upper limit, when x is pi over 4, sine of pi over 4 is 1 over square root of 2. And so that's going to be our new upper limit. So just rewriting this expression, we have the definite integral from 0 to 1 over square root of 2 of u cubed du. Now we have a new definite integral, but this definite integral right here is equivalent to this definite integral right here. And the convenient thing about this is we don't have to go back to x like we did with our indefinite integral, with our antiderivative. So we can evaluate this definite integral as if this was the problem that we were given to begin with. So we would evaluate that by taking the antiderivative, u to the fourth over 4, evaluating that from 0 to 1 over square root of 2. And then we have 1 over square root of 2 to the fourth power over 4 minus 0 to the fourth power over 4. Notice that what we have here is equivalent to, in the other method, what we have here with the minus 0 in there. And so we were able to skip over the part where we put x back in, and then where we substituted pi over 4 and 0 in for our function. So we're skipping over 2 of these steps by not substituting back to x. And then we end up simplifying here and getting 1 over 16. So the key to definite integrals, when we make that substitution from x to u, or any variable to u, is that not only do we replace all the x's in the integrand and the differential, but we also replace the x values on our limits and change them to u values. So the key to this is that we have to change the limits when the differential changes. So when that dx becomes a du, these limits right here need to change to u values instead of x values.